Assalamu alaikum. My name is Sarvan Shah, and today I'll be presenting the topic power electronics and DC motor drives. This topic was a part of my case study that I did for my electrical machines course, and so today we'll be talking about DC motor drives and the components of power electronics that are involved in the creation and the circuitry of such drives. Let us start off by discussing what motor drives are. Well, in essence, motor drives allow us the ability to control certain variables of a motor, such as their speed and their torque, while more importantly, also allowing us to isolate low power control circuitry from the usually high power consuming motors, which could otherwise damage the control circuitry. I was introduced to motor drives in my microcontrollers and interfacing course under the same concept of isolating the power control circuitry from the power circuitry. We used the very popular L298 H-bridge motor driver IC, and then soon following that, I also took part in the National Engineering and Robotics Competition NERC, which required us to design a MOSFET H-bridge based motor driver. And so that basically set the motivation to pursue this project in the first place. So we'll begin with a short discussion about AC to DC rectification, and we will soon learn why it is an important part when it comes to understanding the circuitry that goes into designing DC motor drives such as those that are utilized in industrial applications. So most of the motor drives in this context involve DC motors that are utilized in industrial applications and as such require high amounts of power and often utilize three-phase AC sources. So it becomes important that we have a mechanism for converting these three-phase AC sources into a DC source that can be utilized to then drive the motor. So let us build up on how we would go about converting a three-phase AC source to DC. I'll start with a simple rectification circuit that involves a diode for very basic half-wave rectification, a resistor for current limiting, and a DC voltage source to simulate the back EMF of a DC motor. You can immediately see there are some issues with this circuit. First of all, it has undesirable I square R losses due to the current limiting resistor. The rectification is limited because it only involves one diode and hence we cannot utilize the complete AC cycle. Furthermore, the power delivered is also limited because as soon as the supply voltage drops below the back EMF voltage, the current flow stops. Then we have the issue of the diode's reverse leakage current, which can be undesirable when dealing with high current applications such as those involved in industries. And lastly, it offers no ability to control the power being delivered to the motor. To solve these problems, we have what is called a three-phase 6-pulse rectifier. So we've replaced the resistor with an inductor, and what the inductor does is that it stores the current when the supply cycle is above the back EMF voltage and releases it when it is below. Now this reduces the current ripples. Furthermore, we see that instead of one diode, we have six diodes divided into two bridges, one for conducting each phase's positive half cycles and another for conducting each phase's negative half cycles, effectively giving us six rectified pulses. Now what this does is that this increases our effective average DC voltage that is supplied, and we have a smoother voltage with with a lower ripple. But what's still missing is that one, we have no means of limiting the current, and secondly, we still don't have any ability to control to the power that is delivered to the DC motor. So to solve the challenge of control, we introduce a device called thyristors. Thyristors are devices similar to diodes but operate on a gate firing principle in which a small current pulse on the thyristor's gate terminal enables conduction across its anode and cathode given that the anode is positive. This can also be seen in the figure B below, that as we fire a small current at the thyristor's gate at various angles, a current starts to conduct across the anode and cathode of the thyristor. So you might be thinking how using a thyristor equates to control. Well, what happens is that using a control circuitry, the thyristors are given successive gate pulses in such a manner that it leads to the same 6-pulse rectification. Each thyristor is made to conduct for 120 degrees of an AC cycle, and while each pair of thyristor conducts for 60 degrees. And this basically effectively allows us to utilize both the positive half cycles and the negative half cycles. At maximum capacity, we say that the firing angle of the thyristors is zero. And as we gradually increase this firing angle, what happens is that we see a voltage drop in our output voltage. This animation shows exactly how this rectification works. Now we can see the pulse generator pulses, and now as we start firing successive pulses, we can see that our effective output voltage ripples start to reduce and we have a larger output voltage. The following graph shows us how the output DC voltage varies as we increase the firing angle of the thyristors. So we can see that as it varies from 0 to 90, the voltage level starts to drop, and beyond 90, the polarity reverses. However, this isn't true for a purely resistive load, which would rather just settle to a zero. This animation done on MATLAB also shows us similar results. We see that as we change the firing angle, our effective DC voltage starts reducing to the point that after 120 degrees it settles to zero. So now that we have discussed the power electronics circuitry involved in driving DC motors, we can move on to discussing the various concepts that are involved in DC motor drives, such as one quadrant control, two quadrant control, or four quadrant control. So first quadrant DC motor is when the direction of rotation and motor torque are the same. We start off with a firing angle of 90 degrees, and as demonstrated previously, at this angle the output voltage of the three-phase 6-pulse rectifier is zero, and as such consequently the motor speed is zero as well. As we start decreasing this angle alpha, the speed of the motor increases, or if we start increasing it again, the motor speed will increase again. So what are some of the issues that exist with this form of control? Well, first of all, it involves no mechanism for braking. So suppose you're running the motor at maximum speed and your firing angle is zero. What happens is that if you suddenly decide to change the firing angle and decrease the voltage ED, the motor won't immediately reduce its speed, but rather it will gradually coast back to that speed as the armature voltage of the motor drops. Furthermore, there are issues if we try to operate the motor at lower DC voltages. As demonstrated previously, at higher firing angles, the ripples in the voltage increase, and this increase in ripples contributes to a higher reactive power consumption by the three-phase rectification circuit. The animation also shows us how, as we increase the firing angle, the reactive power consumption increases, and this places a stress on the supply line, and as such, operating a motor using one quadrant control at lower voltages is undesirable and is more suited rather for constant speed applications. And lastly, it also doesn't offer any means of changing the motor's direction. Two quadrant control allows us to cater to the issues of braking by introducing dynamic and regenerative braking. In dynamic braking, we rapidly discharge the armature voltage across a resistor, whereas in regenerative braking, we feed it back to the supply line, and this basically allows us to rapidly drop the voltage across the motor's armature, allowing us to reduce its speed. With regenerative braking or reversing the direction of the motor, there is one issue, which is that it is required that we reverse the armature field, which often has to be done manually and is undesirable in industrial applications. So to solve this issue, we use two rectifiers which run in opposition to each other to enable us to control the motor in an opposing direction without reversing the armature field, hence offering both regenerative braking as well as the direction and torque control of the motor. However, this still doesn't solve the issue of voltage and current ripples at lower speeds and the consequent high reactive power consumption. To solve these, what we have what is called four-quadrant control. This involves utilizing two three-phase six-pulse rectifiers with separate sources. What this allows for us is to have two circulating currents, and this offers more precise controls, even less ripples at lower voltages because of the two circulating currents, and this is the most advanced and expensive form of DC motor control. This was the MATLAB Simulink model that was used to create and generate some of the animations that were utilized to demonstrate and verify some of our findings. Thank you, and for any questions and comments, you can find me at my email, and if I haven't been detailed enough throughout the presentation, then you can check at my report using the link below for more details.